Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the great stuff. This is part of the good stuff. This is the AAS Author Series. And I am super happy to have Raphael Hviding with us today. Hello, Raphael.
Hi, Frank. Thanks for having me. I really appreciate it.
Well, thanks for agreeing to talk about your very awesome article, which we will get to very shortly. And Raphael, where are you located at these days?
I am it was sunny earlier today, but cloudy Heidelberg in the sort of southern Germany area.
Okay, so summer is approaching if it's cloudy then, yeah?
It's definitely starting with spring, but I don't know if I'd quite say that we're in summer yet.
Okay, very cool.
Yeah.
So it is April 30th of 2024 as we record this, and I'm in Phoenix, and we are definitely warming up into our summer mode.
Yeah. I was just in Tucson about 2 weeks ago, and
Oh, nice.
it was hitting the 90s, and I was like,
Yeah,
"Yep, it's hot southwest hot summer right around the corner."
yes, it is. Soon the power switch will go.
Right.
Lovely. Very cool. So did you graduate from Arizona and then went to Heidelberg?
That's right. I did my PhD at the University of Arizona. So I have a lot of fond memories of Tucson, and I was on vacation a couple weeks ago and visiting friends and collaborators. So that's always a
Very
nice
cool.
time. I love Tucson. Yeah.
Very cool. Very cool. Well, congratulations, doctor, on your new
Yeah.
PhD.
Thank you.
Very good. And Raphael, what do you like to do for research?
So I study galaxy evolution specifically from the point of view of active galactic nuclei. So those are accreting supermassive black holes at the centers of most galaxies. And then even further than that, I'm interested in studying them through spectroscopy, especially in large surveys. So looking
Cool.
for large systematic understanding of their populations and statistics and things of that nature.
Very cool. Very cool. And that is going to bring us to this very awesome AJ article. It is open access. It's the open access era, people. Go get a copy for free. Spectroscopic confirmation of obscured AGN populations from unsupervised machine learning. Raphael, take us away.
Yeah, sure. So this work was done in collaboration with my thesis advisor at the time, Kevin Hainline, as well as collaborators of ours out of Princeton University. That's Andy Goulding and Jenny Green. All three of them really fun and exciting people to work with. So if you don't already, I'd recommend it.
Good shout
But
out.
this was,
Good shout out.
yeah, absolutely. Yeah. This is work that we did to sort of tackle the problem of trying to find or characterize AGN populations. And so if you're interested in understanding galaxy evolution, AGN are sort of a pretty essential part of understanding the narrative of how galaxies grow and change over times, what influences when they form stars, what influences the processes that take place throughout their lifetime.
Cool.
Um, but as with every problem in astronomy, if only it were so easy to find these powerful supermassive black holes, that have the light of billions or trillions of suns, you'd think it would be easy to find them. But in fact, because they span a wide range of luminosities and they span a wide range of masses, and of course live in lower mass galaxies with smaller black holes, therefore less luminous, or of course live in obscured nuclei, where whether it's host galaxy dust or circumnuclear dust that's obscuring the sort of UV optical signatures that we'd otherwise expect to see. There's a problem here where in
Yeah.
astronomy we're always biased to find the bright and unobscured things, and but in fact, there's a lot of evidence to suggest that if you're interested in studying AGN or AGNs, I'll probably go between how I say the plural,
Fine.
that the obscured objects may represent a pretty critical phase in the sort of story of galaxy evolution. It's not just a happenstance that they tend to be obscured. It may actually represent some sort of fueling mode
Yes.
or be a combination of the two, right? Nothing is so clear cut as just a random orientation of dust in the line of sight or some sort of cosmic part of some cosmic evolution. So there really is something to be disentangled here that is not so easy to get at, right? Because we're biased against finding them, and AGN by their nature are relatively rare on the sky, and so we have to go out and actually make a concerted effort to find them. And then, of course, the obscured ones get left by the wayside in a lot of instances, right? So,
So what shall we do? What shall we do?
yeah. So one way that the community has tried to find on a large scale obscured AGN is by using the mid-infrared, right? So if we have energy in the optical and ultraviolet that's being obscured by dust, well, then that dust should heat up and reprocess and re-emit this radiation at longer wavelengths. And so space-based all-sky missions, especially the WISE or Wide Field Infrared Survey Explorer, has been absolutely critical for returning sort of samples of millions of AGN candidates by looking for bright infrared sources that are not consistent with dust that's heated by star formation. Now, there's a million caveats and complications and things in here, but it does seem to be relatively it does seem better, for example, let's say, than optical galaxy selection at recovering obscured populations on the whole, but maybe we're still by.
Fair enough. Uh-oh.
Against extraordinarily obscurity and something that's bright to really shine in the infrared.
Cool.
So and I think there's a sentence in here that goes, this bias becomes even more urgent because we're about to get a deluge of
Yes.
optical and near infrared data on huge scales that are essentially, and we're not going to be bolstering our mid infrared capabilities, at least in no missions that I'm aware of, on at least large scales, right? We have JWST MIRI now, but that's never going to be a survey telescope in the sense that it's not going to survey the entire sky. So we're going to have huge volumes of near infrared and optical data that's going to return samples of billions of galaxies, but we're not going to be able to pair those with sort of the next generation of mid-infrared telescopes, as they don't exist, and sort of classical techniques where you follow each one up with a spectrograph are going to start to fail if we have samples of billions of galaxies, right? We're never going to get spectra for them all. So we've been exploring, as I think a lot of astronomers and sort of any scientists or people now are starting to explore, what are ways that we can leverage our data in a more, I don't want to use the word complex, but what are the best ways that we can leverage this vast volume of data that we're now living in astronomy, right? So we have amazing data sets, we have amazing instruments. We have more than we could ever look through ourselves in one lifetime, potentially hundreds of lifetimes. So what sort of computer data-driven techniques can we turn to try and actually tease out and in this case specifically, to tease out a better, more uniform, unbiased selection of active galactic nuclei, such that once we actually have these galaxies, we can fit them into a framework of understanding how they play into galaxy evolution. So maybe that's comparing to simulations, maybe that's direct follow-up studies, but in general, the idea is let's get all the AGN to whatever level we can, and of course, understand the systematics that go into that selection, and then from there we can do a whole bunch more science.
Cool, very cool. I'm with you.
Yeah. So the starting point here is actually with the Hyperzoo PrimeCam survey. The idea is that Hyperzoo PrimeCam, it's not quite a Rubin observatory level survey, but it's still 1,000 square degrees over the entire sky with a similar filter and resolution and depth that you might expect from something like Rubin, but over an area that is more manageable. And again, I'm saying that over 1,000 square degrees. That's still it's still a vast volume of data, but it's not 10,000 square degrees like we're going to start getting with something like Rubin.
Right.
And especially not to even mention the temporal resolution there, but that's for a whole different conversation.
The cadence,
the cadence, exactly right. So the idea is, okay, let's take Hyperzoo PrimeCam data. It's this beautiful data set that we get with sub-arc second resolution, GRIZY colors. It's built to do galaxy surveys and to generate us with catalogs of hundreds of millions or billions of galaxies.
Right.
And then let's actually combine that with the data that still exists from WISE. So the one small distinction here that I'll make, or maybe not distinction, but the one thing I'll draw people's attention to is that if you always think about WISE as a mission that started and finished, it's actually had a very lengthy post-cryo mission,
Yes.
especially in its bluer bands, right? It's 1 and 2 micron bands.
Yeah.
Oh, sorry, it's no, it's got to be 2 and I'm blanking on the exact. It's up above.
Yeah, it's up here. Why?
I think slightly on the page before, but I think 3 and 4 microns.
Here we go.
Yeah, 3 and 5 microns essentially, right? Those blue bands are still continuing to take data, and so you actually get to fairly sensitive measurements in those, though not with the accompanying spatial resolution. And then, of course, the 12 and 22 micron are relatively insensitive, but there's still information there that can be leveraged. And so the idea is if we plug all of the information in, including galaxy colors, galaxy morphologies from the optical, infrared colors where they exist, and let's actually go to figure 2 here. I think that might be the place to kind of show this. Let's go ahead and combine everything into one sort of unsupervised machine learning approach to try and see if we can pick out galaxy populations that are consistent with AGNs.
Okay.
So the trick here is that we're making use of unsupervised machine learning in the sense that we take a huge data set, like I said, it's five photometric bands in the optical, 3 to 4-ish photometric bands in the infrared, all of the colors that you can imagine spawning from all of those colors shaking hands, and then 5 photometric or 5 optical shape information, 5 morphological, there we go, informers from the optical data. Throw that all into an unsupervised machine learning to essentially look for data that are clustered without tagging them ahead of time by we don't tell the computer these are AGN, these are stars. We try and get rid of stars before any of this goes in, but I more mean these are not star-forming galaxies. These aren't elliptical galaxies. The idea is let the computer try and break everything into groups as it sees fit. And then we maybe try and look as to where existing AGN already fit into the paradigm.
Yes.
Especially with attention to obscured AGN. We've had very good success for creating paradigms for basically selecting unobscured AGN, but now the goal is, can we actually do better on the unobscured galaxies?
Yes.
And so here you can kind of see where some of our classes split themselves into in sort of typical optical color, optical mid-infrared color, and also for those that already have redshift space. So for example, the leftmost panel, we can see that the optical magnitude, so how bright these objects are versus their morphology. So objects near the top are relatively diffuse, whereas objects near the bottom are relatively compact. We might compare that to the panel on the right, where just one to the right, where objects in the bottom left corner are blue, objects in the top right corner are red. And so we can see how our selected classes that we're going to be investigating in this work distribute themselves.
Okay.
So we can already immediately see that there's one class that we've picked out. And this is a little bit of a spoiler, but there's one class, this class A, this blue class, which are relatively compact objects that span a wide variety of brightnesses that are all very blue. And so we think, what are blue compact objects in the context of an AGN paper, right? These are going to be those sort of unobscured supermassive black holes where all of that optical ultraviolet light is escaping the nucleus and streams directly to our telescope that we can then observe, right?
Well,
but so that's a bit of a spoiler as to the fact that we're doing a good job at recovering the thing we were already doing a good job at recovering. That's reassuring. What the interesting part are going to be exploring these classes B, C, and D.
Yes.
And seeing what the makeup of those are. And for a little bit of interest, figure 1 shows the sort of what you might expect from the the machine learning product. So if you've never worked with machine learning products before, you sort of get you don't get a typical output space like this where you actually look at colors and magnitudes and redshifts. You actually get some sort of output dimensionality reduced space,
Yes.
where we can separate things in. So figure 1 just demonstrates what that kind of looks like. And then, you look at that and you say, oh, these clusters do seem to separate quite well, but we actually have to go out and do the work and say, well, what are these actually made out of, right?
Yes.
And so that brings us to really the driving force of this paper was that we ran the machine learning, we get the output from these subclasses, and our goal is the gold standard for knowing if something is an AGN or not is to put an optical optical fiber on it or an optical slit on it, take a spectrum and look for excited emission from nebular gas, right? So we want to look for emission lines that could only be excited in the presence of something like an AGN. And so that's sort of your gold standard way of really finding AGN, and of course things like broad emission lines as well, which correspond to bulk motion of ionized gas near the nucleus that would also only be explained by something like AGN activity. So that's where I really got my start in astronomy. As a student and for my while obtaining my bachelor's, I was reducing spectra and looking for signatures of AGN, and here we are, so many years later, doing the exact same thing, just with more of them all at once, and not really no longer by hand. But so, yeah.
Cool.
So we basically take these two classes, or we take these 4 classes, classes A and B, C, and D, and we're going to go ahead and group B, C, and D into one sort of class that we're going to call class 2, and then class A we're going to keep calling we're going to call that class 1. And so if you go to the figure below, you'll see that we basically take these two and we now split them into these respective classes. So we now have class 1, which is just made out of subclass A, and then we have class 2, which is made out of subclasses B, C, and D. Now, this is mostly driven by the fact that because, as you can notice, classes B, C, and D in that first subpanel has much fainter objects in general, around 22nd magnitude. And so in general, we were less successful at recovering spectra for those objects. And so we have to sort of group those spectra together to get results for the overall class. But as well as what we'll notice is that everything in class 1 will eventually be unobscured AGNs, and then I won't spoil what happens with the class 2 objects just yet.
Keep it a surprise. That's okay.
But really, the main highlight of figure 3 right here is these black dotted lines that show where existing surveys for AGNs, and these mostly come from SDSS, at least our comparison point for this work, where these surveys looking for AGNs tend to map in our object's optical morphology space or color space or maybe infrared color space. And so the part that I'll really highlight is sort of the second subpanels, where the black dotted lines live much closer to the bottom left of those subpanels than the entirety of the class. And so in general, the objects that we're going to be looking at are much redder on average than the kinds of objects that have been targeted in the past. And so if your goal is to look for obscured AGNs, objects with dust in the way, it may be slightly promising that the kinds of objects we're getting are on average redder than objects that we've been able to recover in the past. So maybe we're doing a good job, but until I see the spectra confirming what these objects are, I'm not going to, do a jig just yet. We'll get one later. Exactly. Well, no, not to spoil anything, but so this work was done using Hectospec, which is an instrument on the MMT telescope down in Arizona, right? That's and it's a 6.5 meter mirror telescope. And Hectospec is a phenomenal instrument because it's a 300 fiber fed spectrograph. Cool. So you get about 300 optical fibers on a 6.5 meter telescope with about a degree squared field of view. ish, maybe a little less than that.
Nice.
So it's great for, it's a redshift finding machine. It's an emission line finding machine. It doesn't have again, I might complain saying, oh, it can't get all the way down to 22nd magnitude for a lot of objects. But in the grand scheme of things, I think, we can actually do really, really well. So we go ahead and we're going to essentially measure spectra for as many of these objects as we can. And I think we had about four. We had a couple of mishaps with the telescope due to COVID, actually, when these data were being taken. So we had some postponements due to observatory closures, but I think we got about 4 nights or 3 nights in total.
Cool.
Right. So now let's keep scrolling down.
Okay.
And what we'll go ahead and take a look at I think the one with the orange lines, if that helps.
That's the follow-up. Rich.
Yeah.
The orange lines. No orange lines there.
I think that might be on the next page. Here we go. Yeah, this is good. Figure 7.
Yep. Mm-hmm.
Yeah. So these are this essentially figure 7 shows examples of the kinds of spectra. These are, not the kinds, these are the spectra, but sort of the examples of the classifications that we're going to give to our spectra. Okay. So these are all real spectra from our work, along with fits to the data, sort of breaking down the kinds of spectra that we see. And so, for example, in the top row, we're taking a look at unobscured AGN spectra. These are spectra from AGN where you see towards the left-hand side of the plot that rise in the blue emission that's coming from the accretion disk, that sort of characteristic power loss slope that you're seeing, along with these broad emission lines due to gas that's near to the nucleus that has bulk motion that's causing this characteristic broad profile. And we see that we sort of split just to make the stacking easier later, we sort of split our entire sample into the low redshift, and again, that's just redshift less than 1.2, and the high redshift less greater than 1.2 subsamples. Cool. As a counterpart to the unobscured AGN, which are also known as type 1 AGN, we have type 2 AGN on the sort of the row below it, which are these obscured AGN. So AGN where you don't see that blue characteristic power law because that is being attenuated by dust. But same with the close gas to the nucleus, that broad line gas, we don't see those broad lines, but we still see nebular emission lines. And when you actually go and measure or narrow nebular emission lines, when you measure the ratios of these nebular emission lines, they tell you that the ionization of the gas has to be such that it's not compatible with star formation, but consistent more with AGN activity. And so especially in sort of the classic tracer for this are oxygen 3, especially when compared to H beta. Oxygen 3 is a great tracer for AGN activity especially when compared to a weaker H beta. Neon 3 as well, and then neon 5. These are all classic tracers of AGN activity, especially at lower redshifts. And by comparing them to sort of standard lines, H alpha, H beta, oxygen 2, we can definitively characterize what is driving this ionization. And then at higher redshifts, you have magnesium, carbon, helium, etc. These kinds of lines that that can help you, that are good tracers as well for AGN activity.
Very good.
So, for example, we also have examples of star-forming galaxies, right? This is machine learning. This is a statistical thing. We're not expecting to get 100% AGN. The goal is to characterize how many are AGN, right? And then to at least let people decide if that's a good.
Go ahead. Oops, lost a
number or not. Star don't see as strong oxygen 3. We don't see much neon 3 and almost no neon 5. Essentially no neon 5, which would suggest that the driver behind this ionization is almost certainly star formation.
Yeah.
And then we kind of have some weirdos. As with anything, you kind of get some weirdos, whether this is high noise data where we think we found what the redshift is. We think the lines H gamma. There seems to be absorption around magnesium. The slope seems kind of red, but we also have sort of others as well. And in general, we're going to be splitting between AGN and star forming galaxies.
So just to sort of put a number on it, out of the total sample, sort of what percentage is star formation and others?
Yeah, so we can actually come to that in one of the next
okay.
figures.
Okay, sorry.
No, before we move on to that, because that's the great question. That is the driving question. Is we have this whole machine learning algorithm, ideally with the goal of finding. Well, the goal is to find clusters of galaxies, but then we wanted to find the ones that were AGN. And the question is, did we succeed? Are they relatively uncontaminated samples of AGN? And of course, in this case, contamination means star-forming galaxies. But and so we can go ahead and show that in just a second. The one last thing that I'll mention is that all of the spectra here, in order to actually measure those emission line ratios, because we have a decent number of spectra, we use a relatively automated spectral fitting program called Gelato, which stands for the Galaxy Emission Line Analysis Tool. Cool. And so that code was written by myself and formed a big part of my doctoral thesis, and it's available for anyone to use, and it's online, and it's really for recovering spectral fluxes and shapes of lines, especially when you have a large number of spectra where you can't do every single one by hand, right? So if you're talking hundreds of thousands or millions of spectra.
Gelato to the rescue.
Gelato to the rescue, exactly.
Very cool.
So then if we keep scrolling down, we should be able to see some histograms that show us what fraction of our AGN, of our samples are actually made of AGN. And so here you can see some emission line diagnostics. Actually, we might as well stop here. This is sort of kind of answering your question. The blue shaded region on these plots is usually home to star-forming galaxies, the red shaded region to AGN. And within the error bars, we can see that in general, the region of these diagrams that we're populating tends to be the AGN regime.
Yes. Right.
Yes. Many people might be familiar with the BPT diagram, or which is especially for comparing between star-forming and AGN galaxies. This is in general, the BPT diagram has to be used at lower redshift, and so we use some higher redshift analogs like the TBT diagram, and then some UV line diagnostics. So in general, for the BPT diagram, you have to recover H alpha, and we don't go red enough to do so. But just like caveat.
Okay, cool. I'm with you.
Yeah. And so if we keep going down, we should be able to see some histograms.
Here we go.
There we go. So these are, and then we'll have a table in just a little bit, but we sort of do this by objects with redshift and objects without. And again, as we mentioned, class 2 are, especially when we get down to below 21.5 magnitude, hard to recover redshifts for objects that faint with hectospec.
Okay.
But for the bulk of objects that we do, we see that especially if we focus for class 1, it's almost entirely dominated by type 1 AGN, or unobscured AGN.
Right.
So if we think back to figure 3, I believe these were the objects that were all blue and centrally concentrated, right? So no surprise that the objects that our machine learning algorithm likely grouped together because they all shared similar colors, blue colors, and shared similar morphologies, compact. It's not entirely unsurprising that all of these turned out, or a large majority of them turned out to be unobscured AGN. And then for the other classes, sorry, go ahead.
No, it's a good verification, right?
It's a great verification, right? This is absolutely correct. Then for the second class, for class 2, we see that in general, while we do suffer from higher levels of contamination from star-forming galaxies, or objects that present as star-forming galaxies in optical spectroscopy, and I'll sort of draw a little bit more of a, I'll come back to that point maybe in our conclusion, but in general, these tend to have more obscured AGN with some type 1s and a higher contamination rate. So if we go down, I think, to the table that's close, here we should get our fractions for how successful we were.
Right.
So in general, class 2 has about an 85% success rate, right? But 20% type 1, 65% type 2, with about a 10 to 15% contamination rate from star-forming galaxies, or galaxies that we couldn't yeah, maybe elliptical quiescent galaxies, though there weren't many of those in this study, and or
Good.
just galaxies that we didn't characterize as star forming.
Very good. Those are good news.
Yeah, it's great because I think in general, it's large samples of type 2 or obscured AGN are generally drawn from large, unbiased spectroscopic studies, such as the SDSS Legacy Survey, which essentially was a magnitude limited survey where you target some random fraction of everything down to a certain magnitude. And then out of that, your 1% or AGN, and maybe half of those are obscured AGN. And so um, being able to sort of do this the other way around, where we actually start with colors, start with morphologies from large numbers of galaxies, and we can give you a sample of galaxies that we say, hey, we're pretty sure that, especially down to a magnitude of about 20, we're confident that 85% of these are obscured AGN, is already a pretty great way of characterizing these galaxies, especially that we don't require all of them to have amazing, mid-infrared colors that would much definitely require them to be brighter, and also bias them to being obscured or unobscured, or at least luminous AGNs.
Nice. So we have discovery here. It's awesome.
Yeah. So this is especially great if we think about the context of getting billions of data points in terms of spectroscopic, photometric data from the next generation of wide field instruments, near infrared instruments, optical instruments, etc. Rubin, Roman, Euclid. And Roman and Euclid in particular, I might be jumping the gun a little bit, but Roman and Euclid are particular of interest because of that low resolution spectroscopy that they generate from slitless spectroscopy.
Cool. Okay.
And so for those who might be unfamiliar, slitless spectroscopy sort of eschews the traditional idea that if you want to take a spectrum of something, you probably should put an aperture mask on that object, because otherwise you would disperse everything in your field of view. Everything would overlap, and it would be a massive headache. Exactly. But it turns out that with modern computing and people who work to model everything that's going on, slitless spectroscopy has started. I especially think of it in terms of Hubble Grism spectroscopy. Now we're seeing it with J2ST Grism spectroscopy, and now it's going to be included on huge wide field instruments like Euclid and Roman. It might be able to give you just a little bit extra information to really clamp down the true nature of these objects, right? You won't get the same beautiful spectra. Well, at least I think they're beautiful. The very subjective term, but the clean spectra that we saw earlier in this work with those very defined emission lines, but even just a little bit of the continuum shape and potentially some emission lines from things like Euclid and Roman have the power to really, again, from a data perspective, restrict the if you want to think about the space where these objects could be, to allow us to learn more about them. So that's why I think that this is really exciting when we think about the context of what we're going to be able to do next with some of the next generation instruments.
Very cool.
So then I think essentially for the rest of this work, we try and kind of go after that pink fraction there, or not really the pink fraction, the objects that we try and stack a lot of the spectra into sort of respective bins of color and magnitude. And I think I don't want to get bogged down to exactly, at what magnitude, what happens at what redshift, et cetera. But I think there's one plot here that is interesting where we try and really, by using spectral stacking, to try and understand what is driving the red to blue colors of class 2. So if we remember class 2, and we can continue scrolling down because we're going to see a repeat of this insert. I think it's after the big stack plots. This was essentially our relative success of recovering redshifts. But if we keep going down past these plots that are really showing every single stack possible, where we really try and get into the nitty gritty of it for those who might be interested. Right here, this is actually, we'll go down one more.
14.
Yeah, here. This is great. We basically, if we start in the top left, these plots
Mhm.
are really busy. I apologize for that. I did make them all, so it does
All
come
good.
down to me. But we sort of start with this optical color space. All
Mhm.
the objects that are blue live in the bottom left, and
Yes.
all the objects that are red live in the top right.
Yes.
And we see that our study, unlike something like SDSS, in general recovers more red objects.
Yeah.
And so we can split this sample based on a color, right? So that diagonal line is a G minus I color. And we
Mm-hmm.
can stack all the red things and we can stack all the blue things. And we can say, well, what's different about them? What actually drives this color difference? And
Okay.
so on the right-hand side, there's so many blue colors here that maybe I should have done this a little differently. But in general, the dark blue or the solid blue are
Mhm.
the red objects.
Okay.
The light blue are the blue objects.
Okay.
And then the dashed line is if you just apply a basic extinction curve.
Okay.
And so
Interesting.
the idea is that you can take the blue objects, which clearly show that blue continuum,
Yep.
slap an extinction curve on them,
Yeah.
and reproduce the shape of the red objects. And we see that at both high redshift and low redshift. And
Well,
so the idea is that, well, what's driving the underlying color difference between these objects is not a different stellar population.
yes.
It's not a different, there's no galaxy property that's different. It's purely some sort of screen between us and the AGN. Now,
Yes.
this is probably what we'd expect for the unobscured objects, the ones that we're looking at here, because all we're really seeing is AGN light. And so we're either obscuring it or not.
Yeah.
Where it's really, I think, a little bit more interesting is when we look at the type 2 objects or the objects from class 2. So if we scroll down, I think the figure 15, the very next
Yes.
one.
Here we go. Okay.
Exactly this one, yes. Unfortunately, we can't do this comparison at high redshift, but when we do it for the low redshift objects,
What's
the
the one?
ones that are the ones that are redder, right, in that darker red color, are represented, can be represented purely by taking the bluer objects, the orange line, applying an extinction curve, and getting a result of essentially about a magnitude of extinction that we believe it's what's actually driving the color diversity
Cool.
in our recovered
Gotcha.
classes.
Yep. I gotcha.
Yeah, and so that does essentially potentially signal to us that
Yes.
we are actually able to not only recover obscured AGN that are both exhibiting broad lines and not, but actually start to uncover maybe some sort of continua of obscured AGN that potentially would allow us to, again, bringing us all back to the higher level, a goal of understanding galaxy evolution. The goal is not necessarily just to find AGN. I might think that's a lot of fun, but I don't know if the broader scientific community would say that's the end all be all. But if the goal is to understand AGN evolution,
Yes.
being able to understand the continuum of obscured galaxies and then linking that back to other galaxy properties such as age, mass, size, etc., potentially allows us to start going down that path of understanding exactly how AGN fit into this into the evolution of galaxies over cosmic time, and also and sort of vice versa as well. How do the evolution of galaxies affect their sort of AGN?
Yes. Environment.
And
Good.
that's the idea. There's
Cool.
a couple other things interesting in the article for tidbits that people were interested in. We try to characterize some Balmer decrements for these galaxies.
Okay.
Unfortunately, they're relatively noisy, and so we don't get anything that seems to be too conclusive for exactly how much extinction on average we might expect for some of these objects.
A little bit.
But yeah, it's noisy and a little all over the place.
A little scattered, yeah.
But I think that in terms of what we can conclude from this, that I think is pretty exciting is that what I didn't really emphasize in the beginning is that the amount of AGNs that we're able to retrieve is pretty massive, especially on the unobscured side.
Cool.
So when we think about finding, obscured side, when we think about finding unobscured galaxies, typically we think of that as something we can actually do from photometry. And so we can actually get relatively large numbers of galaxies and robust samples, especially SDSS and others. Excuse me. And it's been much harder to build up those same kind of estimates for unobscured galaxies, where we usually have to find them in spectroscopic samples, especially when we talk about galaxies that are AGN in their optical spectroscopy, right?
Okay.
Things like X-rays have been able to do this, but over much, much smaller areas. So in terms
Yeah.
of raw numbers of AGNs, we're actually able to recover a surprisingly large number of unobscured AGNs. So for example, if we think about class 1, it's about 145 AGNs per square degree, where I think something like SDSS would probably be close to 100. Their type 1 or even their entire AGN density is probably something similar to that. I would say about 130, 150.
Okay.
It's again, these numbers are kind of hard to compute, especially for something like SDSS, which has all these different subsurveys, different pointings. But class 2, in fact, would actually represents closer to 200 AGNs per square degree. Again, depending exactly on what reliability we would consider this class to be. But even at an 85% accuracy, I mean, that's still a substantial number of obscured AGNs over the entire sky.
Very cool.
That we actually can now start to unlock with over even larger areas once we start getting data from LSST, or sorry, from Rubin. Rubin's LSST maybe is exactly. And then we're already starting to get some data from Euclid that could already start immediately being able to identify galaxies like this using Euclid. And again, these are the kind of AGNs that have not been really found. Not really found, but on average, we're biased against finding large numbers of them in traditional optical spectroscopic studies, or that have been trained on optical photometry. And so we may not have found the reddest AGN ever. We may not have found only obscured AGNs, but this represents a really powerful way of actually building up large statistical samples of obscured AGNs over large areas of the sky that could be ripe for follow-up. Or even understanding them as they are. And so that's the real power, I think, of what we've been able to, of what me and my collaborators have been able to do in this study. And I think that it's really hopefully paves the way for doing more in the future. Yeah.
We will come.
So that's the sort of punchline.
Very nice. Beautiful work. Beautiful work. Raphael, I want to thank you so much for walking us through your very awesome article. This is great.
Yeah, absolutely.
Sure. And you kind of hinted at it a little bit there at various points, and particularly toward the end. So let me push on that a little bit and ask, where do you think we go from here, given the published article? Are there going to be attempts to push down to fainter magnitudes, let's say in the optical? Are there other machine learning algorithms that could be tried to compare one against the other, et cetera? And so just sort of next steps, where do you think we go with this topic over the exciting coming next couple of years?
Yeah, so there's definitely and will be an effort to push down to fainter magnitudes. So we already have observed using Binospec, which is another instrument on MMT. Smaller field of view. It's not fiber fed, it's slit masked, so it's not as flexible. But essentially but it's a much higher throughput, much higher sensitivity instrument. And so that is the way that we can expand down to, now we're talking maybe 20^2 magnitude.
Okay.
Well, until we publish something, I don't know exactly how deep we've gotten, but we have those spectra in hand, and we can actually go in and go to fainter magnitudes. And again, I want to really highlight that our main comparison point in this paper was SDSS.
Yes.
And as much as I think SDSS, I mean, it's hard put to not understate the importance of SDSS to the astronomical community.
Absolutely.
There's a new kid on the block in the form of the DESI, right? And so we very specifically don't really compare to DESI here, because we want to do that in our follow-up work when we actually have fainter magnitudes. Okay. But and not all the data at the time of writing this was public for DESI. They've been releasing it slowly, but we now have deeper millions of spectra that are, some fraction of it are magnitude limited surveys similar to SDSS that would make a great comparison point for this. So definitely expanding this kind of work to fainter magnitudes is absolutely something we're intending on doing, comparing to public data from DESI, and then using our own machine learning algorithms combined with more sensitive instruments to push down on our own end.
Cool. Very awesome. It's going to be
And then when it comes to machine learning, I think that there is a large amount of innovation happening now in the kinds of techniques we're using. Maybe there certainly are other unsupervised techniques that would be worth investigating. And so I'm excited to see where that goes. But
yeah.
particular in terms of development for what I'm excited about is, I hinted at this before, is really the near infrared slitless spectroscopy that we're going to start getting over large areas.
Cool. Okay.
So currently, a lot of what I work on are pure parallel nearest programs doing slitless spectroscopy. So these are programs where whenever JWST is looking at something else, nearest turns on, takes a dispersed image of a random field of the sky.
Yeah. Okay.
5% of the time you get a bright star and it ruins everything, but the remainder of the time you get a random field of galaxies with spectra.
Nice.
Low to medium resolution spectra, and you can start to characterize galaxies in those fields. And those numbers are only going to explode as we start to see. And I'm also a member of the Euclid Consortium now that I've defected to Europe, and I can join the Europeans. But exactly, yes. But we're starting to see the power of what Euclid can do, and the amount of data but these slitless takes time, it takes concerted effort, it takes careful science, it takes new age data reduction techniques. And so I'm actually really excited about it, about seeing what that will allow us to do in terms of galaxy classification, identification, etc. So that's where I think the future is.
Beautiful. It's going to be a very exciting future over the next couple of years. I'm really looking forward to seeing this field develop. It's great.
Yeah, absolutely.
Raphael, thank you so much once again for walking us through your very lovely article. Appreciate it.
No, thank you.
And that will do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.